All right. Hello. Hi, enthusiastic people. I hope you guys are fit and fine. So, again, this is your physics instructor, Rishabh, and let us continue. Let us continue with our live show. All right. So, I will quickly share my screen and we will begin. Okay. So, with that in mind, let us continue with laws of motion today. Okay. And in laws of motion, I will talk about forces. Okay, so let's first quickly talk about the three laws and then let's talk about the four fundamental forces of this universe. All right, so let's begin with laws of motion and forces. The question is, what is Newton's first law? What is Newton's second law? And what is Newton's third law? Now, many of you might already know the answer. For those who don't know the answer, let me quickly write it for you. And for those who already know the answer, put it in the comment below. Let's start with first law. The first law is also called as law of inertia. This law states that every object continues to be in state of rest or state of motion until and unless some external force acts on it. What does it mean? It says that if an object is at rest, it will like to stay at rest for eternity until and unless some external force applies and push it. That's one scenario. Or according to Newton's first law, if an object is moving, it will continue to move for eternity until and unless some force comes and stop it. For example, this is a block. Okay, this is some object. I take this object and I place it on my hand. Now, technically, this should stay here for eternity until and unless I apply some external force to move it around. Okay. Or let's suppose if you are in space. If you are in space, if you just leave this object here, it will keep floating. Okay, and it will keep floating and until and unless some force like gravitational force pulls it towards itself. That is what Newton said. And if you throw it in space, it will keep moving. It will keep moving until and unless some force pulls it towards itself. That is your first law. Let me quickly write it down for you. Every object continues to be in state of rest, or state of motion until and unless acted upon by an external unbalanced force. Okay, let me give you some example. If you take a blanket and if you just give it a jerk, what's going to happen? The dust particle from that blanket starts coming out. If you have a sofa at your home, which is the sofa contains the layer of the sofa is made up of either cotton or a fabric that is breathable. If you hit on that sofa, what will happen? If you hit on the cushion which is breathable, what will happen? A lot of dust is coming out of it. A lot of dust will come out of it, considering you have not cleaned your sofa in a very long time. Okay, if you have cleaned, you may not get that. But if it's a very dirty sofa, you can just tap on it, or if you just put put some force on it, or kind of slap on it, a lot of dust particle will come out of it. Why? Because those dust particles were inside the sofa and they were at rest. When you applied a force, what did happen? You compress the sofa, you compress the cushion. Okay, but the dust particle like to stay there at their position. So the sofa got compressed, the cushion got compressed, but the dust particle stayed there. And that's the reason the dust particle comes out. Okay. Similarly, with a cloth, if you take a cloth which is very dirty, which is full of dust. Okay. If it is, the dust particles are basically your sand particles or particles which are not sticking to the cloth with via some adhesive. Okay, if you just give it a jerk, what will happen? The dust particle will flow around. Why? Because you applied a force on the cloth, So what happened? The cloth suddenly moved, but the dust particle did not want it to move because they wanted to follow the law of inertia, and that's why they stayed there. Another example of this is if we have a block attached with another block via a string, and if I apply a sudden force, when you apply a sudden force on this, what will happen? These are the two strings, string A and string B. Which of the string will break? Now, usually a person may think that string A will break in the scenario. Okay. But in reality, that is not the case. Why that is not the case is a very good question. This string A will not break because when you apply a force very suddenly, they see that's an important point. It's a sudden force. When you apply a force very suddenly, what happens? That force pulls this bottom block. It's going to pull the bottom block. The bottom block in return will pull the string. Okay, so this string will be pulled. So a lot of tension will be built in the string. So now what will this tension do? This tension will in return pull the another block. Will pull this upper block. Now, this block is directly not in, this block is not directly in contact with the force. Okay, the force is being transferred. So when the force is being transferred, this object will be like, no, I don't want to move. I want to obey the inertia. I will stay here for that fraction of time. So what happens? Because of inertia, this upper block does not move. And all the force that you have applied on the block is just transferred to the string. And that's why the string breaks. Now, the same thing, if you would have applied the force slowly, if you would have increased the force gradually, what would have happened? The force would have transferred to the topmost string. Okay, because the inertia acts momentarily. Okay, eventually the force overcomes. For moment or for fraction of time, it holds. One of another good example is, let's suppose you're in a car, okay, and you're moving with some good speed, and suddenly the brakes are applied. What happens? You lean forward. Had that happened with you? Yes, you lean forward. Now, why does that happen? Because you are moving with certain speed. Okay, your body is in motion. It wants to continue to be in state of motion, but suddenly you apply the brakes. The car stops, but your body is still in motion. Your body obeys the inertia and it continues to move in the forward direction. That's why you lean forward. Okay, that's one thing that is called as your law of inertia. Now, moving on to the next law. Next law is Newton's second law. I know, very creative name. First law, second law. So second law. Now, most of the students get this wrong. Okay, when someone asks, basically this has been my experience. When I ask a student, what is Newton's second law? His or her answer is this: F equals ma. Now, I'm not saying this is wrong. Okay, I'm not saying this is wrong, but I'm saying this is incomplete. This one does not give you an overall picture. Okay, why does it not give you an overall picture? Let me quickly show you. Newton's second law is this: force is proportional to rate of change of momentum. Now, what is this momentum, first of all? Momentum is a quantity given by symbol P, which is mass times velocity. P is equal to mv. Newton said that force is proportional to rate of change of momentum, dp by dt. Or sometimes, if you don't know calculus, if you do not have any idea about calculus, you can also say change in momentum per unit change in time. Rate of change means change in momentum, that is dp, divided by change in time, which is dt. Okay, this proportionality sign can be removed using a constant, and that constant luckily turned out to be a number 1. That's a number 1. So 1 times dp by dt. Now, if you differentiate this equation, d by dt of mass times velocity, if you differentiate the whole equation by the product rule of derivative, you will get mass times dv over dt plus v times dm over dt, which if you write properly, which is m times dv over dt is acceleration plus v times dm over dt. rate of change of mass. Dm over dt is rate of change of mass. Now we assume that mass remains constant. That is what our assumption is. If we assume mass is constant, mass does not change, that means dm will be zero, or dm by dt will be zero, does not change with time. And that's why this right hand side quantity we considered zero. Otherwise, this is your general equation for Newton's second law. I hope this is making sense. Now let me give you a physical approach of the same thing. Okay, how do you visualize Newton's second law? Imagine there's a ball coming towards you. Okay, and you want to catch the ball. You will try to catch the ball in your hand like this. Okay, you're not gonna move your hand. You're just gonna keep your hand like this. The ball came, fall on your hand, fell on your hand, and you just caught it. Okay, that's it. Now this time your hand's gonna hurt a lot. Why? The ball was coming with a very high speed. That means it had a very high momentum. And this momentum, let's suppose the momentum of the ball was 100 unit. And suddenly, in a fraction of time or fraction of second, you just made it to zero. So change in momentum was huge, but change in time was small. So if this quantity, change in time, if this is small, automatically the force will increase. And that's why your hand will start hurting. Now imagine another scenario. Again, you have opened your hand and the ball is coming towards you. Now, the moment the ball touches your hand, you move your hand along with the ball in the backward direction. Now, what are you doing? You want to reduce the momentum. You are reducing the momentum of the ball. So from 100 to 0 you are doing, but your 0 you are doing somewhere around here. You're moving it little back and then you're making the momentum 0. So what you exactly did is you increase the time taken for the momentum to become 0. So that means the bottom term, which is dt or delta t, if your delta t increases, if the delta t increases, if the denominator increases, the final answer, force, decreases. So in this case, when you're moving your hand back, the force reduces that is being applied on your hand, and that's why you don't get hurt. Okay, this is the technique applied by most by the cricketers who do not wear a gloves while catching the ball. Okay, so that times this kind of concept is used. That's a Newton's second law. Now moving on to Newton's third law. Newton's third law. This one is everyone's favorite. This is called as law of action and reaction. Law of action and reaction. What does it mean? I also like to call it as law of karma. Okay, so basically it says that every action has an equal and opposite reaction. Every action has an equal and opposite reaction. Opposite reaction. That means if you keep a ball here, or if you keep an object here, a block here, what is it doing? It has some weight, it has some mass. So it's applying gravitational force on the ground. So Fg amount of force is used to push the ground. So the ground in return pushes it back with a normal force. We also call it as Fn sometimes. Let me write it as Fn only. This is your normal force. So this is your action force and this is the reaction force. For example, I'm holding this object. This object is applying a force in the downward direction on my hand. So my hand in return is applying an upward force. Let's suppose if you're pushing a wall. When you're pushing a wall, you're applying a force on the wall. Now, technically, since you're applying the force, this wall should move. If the wall is not moving, you are applying the force. The wall in return is applying a force back on you. Okay, so there is an action and reaction force. Okay, it's always in a combination. Alright, so that is the 3 types of laws that we have. Now, let me quickly give you an introduction to the fundamental forces that we have in this universe. And in the next session, we will be talking about the forces that we use in Newtonian mechanics. Okay, so let me quickly do that. Fundamental forces. Now, how many fundamental forces do we have in nature? If you know, then you can comment down the number of forces, and if you know their name, that's even better. So make sure if you know the names of the forces, please comment down. If not, you will know in a moment. So the first force that we have is, does anyone want to take a guess? Gravitational. Gravitational force. This is the longest range force. That means it acts at a very large distances. Even if the object is like thousands of kilometers, 2000, so look at the distance between Earth and Sun. It's like 1.4 billion kilometers approx. Okay, that much amount of the distance it has, and still the Earth is being pulled by Sun's gravitational force, right? So it's a very long range force. It acts between masses. If you have two mass, m1, and if you have another mass, m2, they will attract each other with the same force. So even Earth is attracting Sun. Okay, it's not just the Sun that is attracting Earth. No, Earth also attracts Sun. So that's your gravitational force acting between masses. Then the next thing that you have is electromagnetic force. Electromagnetic force. Now, gravitational force acts between masses. Electromagnetic force acts between charges. So if you have one positive charge, another positive charge, they will repel each other with a force. That's the force of repulsion. If you have a positive charge and a negative charge, they will attract each other with the same force. And if you have two negative charges, what's going to happen? Yep, they will repel each other. That is your electromagnetic force. Now, what is the next force that we have? By the way, this electromagnetic force is a very short range force. Okay, and even shorter than this is your next force, that is called as strong nuclear force. Strong nuclear force. There's a reason why we call it as a strong nuclear force, because reality in real life scenario, or the truth is, this is actually very, very strong force. Let me give you an example. You cannot take two positive charges and, bring them very close to each other. They will definitely repel each other. But if you observe a nucleus, what is nucleus made up of? Does anyone know? If you know what is nucleus made up of, comment down. If not, let's have a look at it. Nucleus is made up of these particles. Let me quickly draw this one here, maybe one here I'll put, and one here I'll put. These are P's and these are N's. Da, 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 and one here. Maybe I'll put one here as well. So these N are called as neutrons, which are neutral particle, and these P's are called as proton, which are positive particle. Now, nucleus is very, very small. How small it is? It is of the order of 10 to the power minus 15 meter, 10 to the power minus 15 meter. That is the order of a nucleus. That's small. That's much how small it is. You want to keep charges this much close to each other, and that's very difficult. You need a force which is really super strong to hold the nucleus. And that's what your strong nuclear force is. It is holding the whole nucleus together. Okay, so the force that holds the nucleus is called as strong nuclear force. Now the next one, the last one, is called as weak nuclear force. This force is basically associated between the conversion of proton to neutron and vice versa. So there are many processes. One of them is the conversion between proton and neutron. Proton can become a neutral particle and neutron can become a positive particle. Okay, it is possible. Now, during this process, the process that carries out this kind of transition or this kind of conversion is called as weak nuclear force. There are certain parameters which you may not know, or there is something called as bosons. Okay, bosons are the one. There is something called as W boson and Z boson, which are involved in this process. But what we need to understand is that weak nuclear force is the force which carries out the conversion process between the proton and a neutron. So that this is the whole overview of the fundamental forces and the Newton's laws of motion. In the next session, we'll be continuing about with the Newtonian forces that we require in our day-to-day life. We'll be discussing the overview of all the forces, and then we'll be talking about them in detail, step by step. So I hope whatever we have done today is clear to you. And yeah,